We're going to be looking at how we can identify and calculate stationary points of a function. So a stationary point is where our derivative of our function is equal to 0 at a particular point. So this is where our function is neither increasing or decreasing. So having a look at this graph over here, we can see that we've drawn a tangent line here. And as this tangent line is horizontal, this represents a 0 slope. So this means that the instantaneous rate of change, or the derivative at this point, is also equal to 0. So our stationary point can also be something called a turning point. So a turning point is where we see our signs change from a decreasing to an increasing value. Okay, so on this side here, we can see that my function is going from decreasing values. Okay, it's getting onto that stationary point here, and then it's changing into increasing values. So this is how I know that this is a turning point. Okay, because this is going from decreasing to increasing values, I can also see that this is a local minimum. Okay, so this means that all the value at this point here is the smallest in the local region surrounding it. Whereas if we had our function that was increasing and then it got to my stationary point and then it was decreasing, then I'd have a local maximum here. It is important to be aware, though, that all stationary points are not turning points, but all turning points are stationary points. And we can see that looking at this example over here. So I can see that my graph on this side of my stationary point is increasing. And then I get to my stationary point here where my tangent line is equal to 0. And then on the other side, my graph is continuing to increase on the other side. So it hasn't actually turned from an increasing to a decreasing function or vice versa. Instead, it's gone from an increasing function, our stationary point, and then it's continued to increase on the other side of that stationary point. So this is known as an inflection point or a saddle point. Okay, and of course this would be the same as if we had a decreasing function, then we had our stationary point, and then a decreasing function instead on the other side as well. To find the stationary point of our function, we need to evaluate our derivative when it is equal to 0. So we'll use first principles, or using our power rule, we'll find the derivative function, and then we will make that equal to 0 to find at what point or what x value is my derivative equal to 0. So this x value that we find for our derivative when x it's equal to 0. This is called our critical value. So this is the value of x where my derivative is equal to 0. So we can use this critical value to actually determine whether or not our stationary point is a local maximum, a local minimum, or if it's an inflection point. So to do this, we have 4 different cases. So in this first instance here, okay, once I found my critical value x when it's equal to a in this case, I'm going to put this onto a sign diagram. So I've drawn up my sign diagram here and I've put in where my critical value is. I'm going to plug in values into my derivative function, okay, that's on either side of my critical value. So on the left-hand side, I will put in values that is less than the critical value to see what is occurring on that side of my function. And then I'll put in values that is greater than my critical value so I can see what is occurring on my other side of my function so that I can determine exactly what kind of stationary point this is. So in this first case here, Okay. We found that by plugging in lower values on the other side of my critical value, my derivative function was positive. So we know from 1.5 that if my derivative value is positive, that means my function is increasing. So on this side of my critical value, my function is increasing. And on my other side of my critical value, we've plugged it in and we found that my derivative function greater than my critical value is negative. So because it is negative, we know that a negative for our derivative function means that my function itself is decreasing. So we're going from an increase to a decrease, so this must be a local maximum. Looking at our next case here, my local minimum. So plugging in, we found that on the left-hand side of my critical value, the derivative value was negative, so I'm decreasing. I get to my stationary point, and then I've plugged in some more values, and I found that my derivative function on the other side of my critical value is positive, so I know that my original function is increasing. So we've got our local minimum here. If I find that on either side of my critical value, my function or my derivative function is positive, either side, that means that my original function is increasing on the other side of my stationary point. So I know that this is an inflection point. And the same vice versa, that if I find on either side of my critical value, if both of my values for my critical function from my critical value of the derivative, it's negative either side, then I know that this is also a point of inflection too. Next, we're going to be going through a few examples in your booklet, but I do encourage you to try and these questions yourself first before watching me do them, as it will really benefit your learning.
This example is asking us to find and classify the stationary points of our function. So remember our stationary points here. We find this when our derivative of this function is equal to 0. So the first thing I have to do is actually find the derivative. So f dash of x is equal to, now I'm going to use the power rule for this. So I've got 3x squared plus 6x take 9. So there's my derivative function, and now I'm going to have this equal to 0. So I'll get 3x squared plus 6x take 9 is equal to 0. So now that my derivative function is equal to 0, I want to find at what point or what value my x is to be equal to 0. So first I'm going to factorize, and I'm going to take out a 3 first. So I've got 3, and inside my brackets I've got x squared plus 2x, and then that should be take 3 is equal to 0. And now I've got to find two numbers that if I multiply them together, it's going to give me negative 3. And if I add them together, it's going to give me 2. Now, the only number I can think of, or the only two numbers that I can think of that's going to give me this is going to be, should be 3 and negative 1. So fully factorizing this expression now, I'll get 3 and I'll have x plus 3 as well as x take 1 equal to 0. Now for my x's inside my brackets to equal 0, I need to have my x equal to minus 3 and my x equal to 1. So these are my two critical values that I'm going to put into my sign diagram. So my sign diagram of my derivative. So I'm going to rule a nice straight line, and I'm going to place both of my numbers onto this sign diagram. So minus 3 is going to come here, and my 1 is here. And now I'm going to plug in values that is less than minus 3 to see if I have a increasing or decreasing function, in between minus 3 and 1, as well as greater than 1, so that we can actually identify what kind of stationary points that we have at both minus 3 and 1. Oops. So I am going to first start with between minus 3 and 1. So I'm going to plug in the value of, I reckon, 0. So let's get rid of this dot here, and I'm going to plug in 0. And I can see that if I plug in 0 into my initial derivative function up here, I'm actually going to be left with a minus 9. So this point, or this part in between my minus 3 and 1, because my derivative function is negative, I know that my function itself is decreasing at this point. So now let's plug in a different value. So I'm going to look at less than minus 3. I'm going to go minus 5, just because it's a nice number to deal with. You can do any number you want. So I'm going to go 3, and then I've got minus 5 squared plus 6 times by minus 5, take away 9. So remember, I've plugged this into my derivative function. And this is going to be, minus 5 squared is 25. So 3 times 25 is 75. Plus, now I've got 6 times by minus 5. So that should give me minus 30. Take 9. And I can see here I've got 2 smaller lower values, so that'd be technically take away 39. So I've got 75, take 39. So I know that this is going to end up giving me a positive number. Okay, so I know at this point, less than minus 3 of my critical value, my function is increasing. And finally, let's plug in our last number. So we might plug in, instead of 1, we're going to go a bit higher, so I'm going to go 2. So plugging this into my derivative function, this is going to be 3, and then I've got 2 squared plus 6 times 2, take 9. So this is going to be 2 squared is 4, and I guess 4 times by 3 is 12, plus 12, take 9. So I'm going to have 24 take 9, so of course that's still going to give me a positive over here. So now that we've completed our sign diagram, we can actually classify our critical points. So having a look at my minus 3 over here, this critical value, I can see that on the left-hand side, my function is increasing. It gets to that stationary point, and then it's decreasing. So I can see here that at minus 3, I have a local maximum. And having a look at our minus 1, oh sorry, not our minus 1, just our 1, I've got a function that is decreasing. It gets to my critical value at 1 where it's stationary, and then it's increasing. So here I can see that I have a local not local maximum, a local minimum. Okay, so I can say that therefore we have stationary points at x equal to minus 3 and 1, and we can see that x equal to minus 3 is a local maximum, and x equal to 1 is a local minimum. Oops, that's not how you spell local. Alrighty, now we finished the question, so we're going to have a look at our next example. This example asks us to find a, b, and c of this equation, y is equal to x cubed plus ax squared plus bx plus c. And we've been told that it passes through 0, 5, and that it also has a stationary point at 2, 7. So the first thing we're going to do is we're going to write down some of the key bits of information that we have. So I know that my equation passes through when our equation is equal to 0, it's at 5. And I know that when my equation is equal to 2, my equation is at 2, my function is equal to 7. So this is the points that it's passing through. I've also been given its stationary point as well. So I have a stationary point at my f dash of 2 equal to 0. Because remember, for our stationary points, my derivative has to be equal to 0. So we've been given some values for our function at different points, and we've also been given a value for our derivative. So the first thing that I think we should do is actually find, well, what is the derivative of this function? So my function being x cubed plus ax squared plus bx plus c. I encourage you to pause this video and actually figure out, using the power rules, the derivative function. So for myself, my f dash of x is equal to 3x squared plus 2ax plus b. And I know that I've been given my f dash of 2 equal to 0. Okay. So what I'm going to do is I might actually plug this into my derivative function and maybe see if I can try and find maybe possibly a starting point. So if I put in f of 2 is equal to 3 times by 2 squared plus 2a times by 2 plus b. And we know that this is equal to 0, so therefore I've got 2 squared is 4 times 3 is 12 plus 4a plus b is equal to 0. And I can see I've got a singular b here, so I'm going to have rearranged this equation so that this b is by itself. So therefore, I know that my b is equal to minus 4a take away 12, just by rearranging. So I've got one key bit of information here. The other thing I know as well is that if my original function is equal to 0, so the function up here, I know that if this point here is equal to 0, I might plug that into my original equation right here and see if I can actually determine maybe what one of my points are. And I can see that if I put 0 into this function here, I should actually be able to find a value for my c. So let's give that a try. So given that my f of 0 is equal to 5, so that was one of those stationary, that was one of the points that it was passing through that we've been given. So plugging that into my original equation, so I'm going to have f of 0 is equal to 0 cubed plus a 0 squared plus b times 0 plus c. And I know that this is equal to 5, sorry. So therefore, C is equal to 5, right? So there we go. There's another key bit of information I've got as well, where my C is equal to 5. So that's handy. So I'm actually just going to plug this straight into my original equation. However, let's see if we can also use this point up here. And maybe we can see if we can get a value for maybe either my B or my A. So I've got my F. So I've got my F of X is equal to X cubed plus AX squared plus, and then I've got BX plus C. So I did find that earlier on my B here was equal to this minus 4A take 12. So I can see that if I replace this B over here with this expression up there, then maybe, knowing that I also have a value for C, I could potentially solve for my A here. So if I have my F of X is now instead equal to X cubed plus AX squared plus, and I'm going to put in this B value instead, so minus 4A take 12 X. And instead of this C, I'm going to put in 5. So there we go. This looks starting to get somewhere. So now if I simplify this a little bit further, I'm going to have F of X is equal to X cubed plus, and then we'll have AX squared, and then I'll have take, and remember I'm going to have take 4A, so this probably still have to be in brackets at this stage, so take 4A plus 12x plus 5. Now, we were given another point up here, which was my f of 2 equal to 7. So I'm going to plug this in here, as I can't really plug in this f of 0 equal to 5. Otherwise, I can see here that this expression over here will go away, as well as this one, and we'll be in the same boat where we only have this 5 left. So we're going to plug in our other point that we've been given. So given that my f of 2 is equal to 7, we're going to have f of 2 is equal to 2 cubed plus a times 2 squared, take 4a plus 12 times by 2 plus 5. And we know that this is equal to 7, so therefore I know that 2 cubed is 8 plus 4a. Now 2 times by 4a is 8a, so take 8a. And then 2 times by 12 is 24, so take 24 plus 5 is equal to 7, as we have been given from here. Now simplifying this, we're going to have that 4a take 8a, that should give us a minus 4a, minus 24 plus 5 is going to give me a minus 19. Take a further 8 gives me minus 11 is equal to 7. So just making sure that my equal signs stay aligned. And getting this 11 to the other side gives me minus 4a is equal to 18. And then a is equal to minus 18 on 4, which of course simplifies down to minus 9 on 2. So there we go. Now we found the value for our a. So because we have this a down here, I can actually use my b up here to actually solve for what b actually is. So coming back down here, I can say that my b, so therefore, so I can say therefore my b is equal to, now that was minus 4 times by minus 9 on 2, take 12. So this is going to give me 18 take 12. And then 18 take 12 is equal to 6. So finally, we've actually got a value for our b, which is 6. So we can plug this all into our original equation up here. To complete our question. So this tells us that my f of x is equal to, a was minus 9, oops, sorry, no it's not, it starts with an x cubed. So x cubed plus minus 9 on 2x squared plus 6x plus 5. So there we go. There is my final answer.